So this would be from chapter 7. Thing here, A, how much work is done by friction, question mark. Having a total mass. Alright, so we're given a mass, 90 kilograms. We got a slope, beta was 60 degrees. We got constant speed, coefficient of friction. Coefficient of friction is that mu.
0.1.
And how much work is done by friction? So and then going to our equations, chapter 7. Shall I write all the equations in green, or for each chapter do a different color?
Each chapter is a different color.
Yeah, I think that would help. Alright, so and then chapter 7.
Hold on. I'm gonna have to help you out. You ain't got no, you ain't gonna have no space on the board. Do we still need this right here?
That's from chapter 9.
I know that's chapter 9, but like you should rewrite it.
The torque. Yeah.
I was like, you gotta erase it out.
Definitely don't need that.
Or you could put chapter 7 and 8 over there. No, 6 and 7 over there, and then 8 and 9 right there, and keep the middle of the board. But you have to rewrite it, make it smaller.
And then this angular acceleration, that's from chapter 10.
Yeah, you should like leave that on the end soon.
Alright. So to the left of the angles. Alright. So chapter 7, we got work. F D cosine theta. Guess I could put one, we got a joule. 1 Newton meter, which is equal to kilogram meter squared per second squared. And then might as well put the other ones. Kinetic energy.
So there's a weekend. Study. We'll go back tomorrow.
Yeah.
We'll go next year.
So the next part, how much work is done by friction? So we just need to do the FD cosine. from our equation, W equals F D cosine theta. A distance. So now I need to put the F being the mu mg. I wonder if I need to put that in our equations. Oh, it comes from the normal force. Force of friction equals mu times n. Yeah, you probably need that. Force of friction. Friction equals mu times n. So we got friction equals mu times n. So my force of friction is mu times n. And then I put in d cosine theta. But my normal force, what's normal force equal to? If I have this here.
What's the revenue? Is that the force that the mountain, whatever, is acting on the skier?
It's similar to what you were saying about the gravity, because normal force, like if I have a book on top of the table, the normal force is the force that the table is exerting up, and then of course you got the force that the mass times the gravity. So normal force should be the opposite of that. But for this one, since it's at a slant, my normal force is gonna have to be so mu. So I know mg, but what do we need to do when it's at a slant in order to solve for the x component?
Divide computer ratio. Sweet.
So that's mg. In order to solve for this,
Yeah, close that.
yeah, there we go. mg cos. But this one, yeah, it's still of the tangent. It's still of the slope. And then you still gotta put in d cosine theta.
You gotta divide what form?
Yeah, it'll still be multiplied. Cosine of Phi. Yeah, so there is a different angle. This angle is phi. And then this angle is theta. So this angle is phi, which is the 60. And then this angle so in order to solve for this angle, it's a straight line here. So that's what's gonna give away what angle I need to use there. It's gonna be cosine of the straight line. So we got mu mg cos 60 e cos. So that's actually 180. Because there's a, see here is 60 degrees, but then because this is a straight line, force of friction. 120 minus 60. Nah, we'll have it as 180.
Put the distance in there.
Yeah. So and then we're able to put in everything that we have here. So we got the mu, we got the theta. So and then we had to. So this actually needs to be phi. Because in our oh, they don't say. It would be nice to have that distinguished. But that's phi. Our theta is gonna be 180. Because the force of friction, here's why it's 180. Because the force of friction is going up. It's along this line. There's the force of friction. Because it's along this line, it's actually going to be the 180 because it's going along that line. So the work done by friction, the distance that it's traveling is traveling along that straight line.
Oh, okay.
Yeah, that's what it's. That's
what
what makes
it.
it.
It's supposed to be like a straight line. Okay.
Yeah, that's what makes it kind of confusing. Alright, so we have the work of friction. Then we have to add up. We have work of tension. So the B, how much work is done by the rope on the sled. So that's tension. So B, how much work is done on the rope. So WR question mark. So instead of this F, we're gonna put tension. Yeah. T D cos. this will actually be feet. It'd be nice for them to use. See, that should be feet. Oh no, that's still theta. Because that's being over there. Alright, so anyway. So now it's tension times the distance. The force of tension is very similar. So the way we solve for tension, so tension plus the force of friction is mg sine of that's the work done by friction, and then you have your tension. So we put that in that equation. And then there's also the force of friction. So we can add those up. And then it's mg sine of theta. Mg sine of theta. So that part, tension. So then we have to relate that with friction. Tension plus friction. Put that tension plus friction. Oh, maybe that's why. X. Yeah, so that's why, because it's the y. So this is going to be tension force as well. So tension plus friction equals mg sine theta. So this is probably the more difficult part of that one. The tension plus the force of friction equals the mg sine of phi. So this is the y direction of the phi angle. So that way, because I know my force of friction, so now I'm gonna put in T equals the force of friction times mg sine of phi. And then I still gotta put the d cosine theta. Mg sine of phi minus force of friction friction, mu mg times cosine of mg sine of phi. Oh, because I said force of friction mu times n, so I can put mu so I can put mu mg sine of phi, and then it's mu mg. Alright, so this is the part I gotta put minus, so we can understand that t equals mg sine of phi minus f. So that's where that came from. Make sure that looks good. Yeah, so this is definitely probably the hardest part of that one. It's just putting you're just adding up the tension and friction together here. Like, we know tension and friction are both together, so T plus F equals the forces in the y direction, mg sine of phi. So that's how we know what T is. T must equal mg sine of phi, and then bring F over minus F. And then we said F equals mu mg cosine phi, which is right here. Mu mg cosine phi. So now I can put those. So that's just my T. And then I still need to put in D cosine theta. I can pull these together. Mu mg times sine of phi minus cosine of phi. And then still d cosine theta. So now we have everything for that. Yeah. So that's the hardest part right there, is to make sure that you add up the tension and friction. All right, see the work done by gravity. It's pretty much the same thing. And then, so yeah, we pretty much got through everything there. Cause it's the same approach. The FD cosine theta. Put that down here. See. Work of gravity equals that cosine theta. Here's the force of gravity. Mg. What's the total work done? You just add them all up. Work of friction plus the work of rope plus the work of gravitation. So that's that. If there's a way I could make that faster. All right, moving on. 7.3, we had example of 7.7, and then we'll be in 8. Now, I don't know if we need to do 9, we went over 9